So this work is related to dilatant properties of low molecular weight polyelectrolyte. And what I am investigating with classical molecular dynamics is the viscosity of polyelectrolyte as a function of the shear rate. So in what is called constant shear simulations. And actually, the kind of simulation I'm considering is simulating a quake flow. So this work has been done at the University of Tsukuba, and I am working for RIST, which is based in Tokyo. So to start, yes, this work is related to shear thickening fluids that are smart structural materials. And what we are seeking for is resistance to external mechanical stimuli like impacts, because it is important to protect integrity of structures, like for the space station, because in space there is a large number of debris, and that can affect the integrity of the whole structure if there is some collisions. Also, it can be used to protect bodies like in liquid body armors. So here you can see short movies showing an untreated fabric and a treated fabric with shear thickening fluid. So you can see that it can protect from stabbing, and it can protect also from bullets. And usually shear thickening fluids are made of a dispersed phase, often silica particle in a continuous liquid phase. And in my case, I am considering the following of experiment of Takeda et al., where they have made a shear thickening fluid made of polycation, polyanion, and water. So it's anaceous mixtures. For polycation, they considered poly-2-methacryl low eloxy ethyl trimethylammonium, and for polyanion they consider polyacrylamide coacrylic acid. And in their experiments, the mole ratio of polycation over polyanion was 1/4. And what they observe is by using this aqueous solution, by shaking the liquid, they were observing phase transformation from the liquid to a gel. And that can be monitored. That can be observed on the complex viscosity as a function of time, where you can see the sharp increase of the complex viscosity due to shear thickening. And what I'm trying to understand in this research work, in this kind of simulations, is underlying molecular mechanism of shear thickening, and I try to understand the role of each fluid species in such kind of simulations. And in such kind of system, And for that, I use non-equilibrium molecular dynamics combined with SLOD algorithm in order to shear the system. And I have used profile unbiased thermostat to keep the temperature constant in the course of the simulations. For the simulation, as you can see here, it's a simple shear where we apply both a velocity gradient with a top velocity ranging from 10 to the minus 5 to 0.9 angstrom per femtosecond, and that corresponds to macroscopically to 1 meter per second up to 90 kilometer per second. So 90 kilometer per second is a bit high, but this is the kind of range you can expect for bullet for velocity of bullets, for example. And what I am doing is that I am monitoring the viscosity as a function of the shear rate. That can be defined like this. It's the ratio of the top velocity in the velocity gradient over the length of the simulation box. For polycation, I have considered a low molecular weight polycation with a molecular mass of 518 gram per mole roughly, and for polyanion, I considered a molar mass of 428 gram per mole, and the charge of each polycation and polyanion is respectively plus 3 electrons and minus 3 electrons. And also I added some water molecule within the system. For the force field, I use the general Amber force field and Mulliken charges. So in that case, for Mulliken charges, they were computed from the Amber tool program, and those partial charges were computed at the ground state. And to compute those charges in Amber tools, I use a semi-empirical minimization step that use a conjugate gradient to get the partial charges. And for the water molecule, I use a well-known and classical force field, which is named SPC-FW, which is a flexible force field for the water molecules. So in that case, I'm considering small molecules, and it means that charges are highly concentrated within polycation and polyanions. And finally, the last thing to say about those molecules is that the weight of polycation and polyanion stand for 20 weight%, of the whole molecular system. So from such kind of system, and you can see some snapshot of those molecular system with water molecule and without water molecule, and red stand for the polycation and green stand for the polyanion. And from this equilibrium state, I started to shear the system by applying a simple shear. And from those shear simulation, I monitor the shear viscosity as a function of the shear rate. And on this graph, you can see the shear viscosity for neat polyelectrolyte in green, which is green field squares. You can see also result for aqueous polyelectrolyte, which is red field diamonds, and result for pure water, which is blue field circles. The line and the dashed line, dotted line, and dotted line stand for different model I use to characterize shear thickening in this graph and in my system, and to characterize also shear thinning. And what we can observe from this slide and from this graph is that the green data, so neat polyelectrolyte, behaves like a yield stress freeze. So there is no plateau at low shear rate like you can observe for aqueous polyelectrolyte and pure water. Starting from the beginning, shear viscosity is decreasing with the shear rate, so there is a shear thinning effect. Then a minimum is reached before rising again, which has to be related to shear thickening. And using models and also simulation data, I was able to estimate the yield stress of this yield stress fluid, and I estimated about 270 megapascal. Then mixing polycation and polyanion with water, I was able to observe the behavior as shown from red data. And here you can see a plateau regime which has to be related to the Newtonian regime. Then viscosity start to decrease, which is shear thinning. Then it reaches minimum, and then viscosity starts to rise again, which is due to shear thickening. And using the cross model to describe shear thinning, we had a very well description of shear thinning and of the plateau at low shear rates using the cross model in that case. Also, what we can see is that dilatancy for polyelectrolyte-based system for the green data and red data is observed, and also the more the water molecule within the system, from neat polyelectrolytes, so green data, to blue data where it is pure water, we can see that the more the water content within the system, the less viscous the system is, with a decrease of the shear viscosity overall. Then, in order to understand the effect of the shear thinning effect in such kind of simulation, I started to investigate molecular structure from molecular simulation and molecular trajectories. and I focus mainly on the aqueous polyelectrolyte, which is the main interest in this kind of simulation. And I use cluster size analysis, and in that case I consider two molecules being aggregated when two atoms belonging to two different molecules when they were within a radius cutoff radius, what I called R cluster in this cartoon, and the distance I chose is 0.35 nanometers. So when two atoms are within 0.35 nanometers, they are considered as aggregated for the molecule. And you can see on this snapshot, molecular snapshot, where there is different colors. Each color was attributed to a different cluster, and colors were arbitrarily given to clusters. And when I increase the shear rate from low shear rates, which is state number 1, to high shear rate, which is state number 4, what you observe is that there is more clusters, so more colors within the system with smaller sizes. So the area taken by each colors is decreasing in size. So this is that depart from the classical pictures of shear thickening in conventional solution. So we had to understand the origin of this shear thickening, and what I did is I monitor the potential energy as a function of the shear rate. And you have the potential energy for the pure water system, neat polyelectrolyte, and the aqueous mixture of polycation, polyanion, and water. And there is a different contribution, including van der Waals interaction, the Coulomb part of the Coulomb potential, so at short distances, the long term in the Coulomb potential, molecular energy, which is internal motion with bond bending, bond stretching, etc. And you have the total contribution. And what I observe is that dilatancy originates from intramolecular energy in polyanion and polycation, and from van der Waals interaction in water-based mixtures. So to summarize what I said, we have seen for viscosity data that the lower the water content, the higher the viscosity. That dilatancy was observed for neat and aqueous polyelectrolyte at high shear rates, and this dilatancy arises from intramolecular and van der Waals interaction within my system. So thank you for your attention. I would like to acknowledge my sponsors and computational resources. And if you want to know more about this research work, you can check this paper in the Journal of Physical Chemistry B. Thank you very much for your attention.